Underneath a quiet stretch of forest and geysers in the American West, there is a chamber of molten rock large enough to bury entire states in ash. It has erupted before. It will erupt again. And when it does, the country living on top of it may not get more than a few weeks of warning. This is the story of Yellowstone, and the eruption that scientists say is not a matter of if, but when. Most people who visit Yellowstone National Park come for the wildlife, the waterfalls, and the geysers that erupt on schedule like clockwork. They walk along wooden boardwalks, snap photos of steam rising from the earth, and leave without ever knowing what lies beneath their feet. What they are standing on is not simply a park. It is the surface skin of one of the most dangerous volcanic systems on the planet, a supervolcano whose true scale is almost impossible for the human mind to grasp. Beneath the park sits a magma reservoir stretching roughly 45 miles long and 18 miles wide, filled with enough molten and partially molten rock to fill the Grand Canyon many times over. This is not a mountain waiting to spew lava down its slopes. It is a caldera, a vast crater formed by past eruptions so violent they collapsed the ground itself. And here is the detail that unsettles even seasoned geologists. The boundary of that ancient collapse is so enormous that most visitors driving through it never realize they have entered a volcano at all. The rim of the caldera stretches across valleys, mountain passes, and entire river drainages, so vast that it can only truly be appreciated from the air or from decades of careful mapping. To understand why this matters, you have to go back in time, deep into the geological record, to a place most textbooks barely mention with the weight it deserves. Roughly 1 million years ago, the ground beneath what is now Yellowstone tore open in an eruption so powerful it ejected around 2,450 cubic kilometers of material into the sky. To put that in perspective, that is more than 2,000 times larger than the eruption of Mount St. Helens in 1980, an event that already flattened forests and killed dozens of people. Ash from that ancient Yellowstone eruption did not just fall nearby. It blanketed a significant portion of North America, reaching as far as the Gulf of Mexico. Entire ecosystems across the continent would have been buried under choking gray dust within days, long before any human being existed to record what happened. Then, roughly 3 million years ago, it happened again. A second cataclysmic eruption, smaller than the first but still monstrous by any modern standard, reshaped the landscape once more, carving out new depressions in the earth and rewriting the region's geography entirely. And then, about 640,000 years ago, came the eruption that created the caldera tourists walk through today. That event released enough volcanic material to bury an area the size of a small country under meters of ash. The eruption was so massive that it triggered the collapse of the ground above the emptied magma chamber, forming the very basin now dotted with hot springs and geysers. Where visitors now stand to photograph bison grazing in open meadows, the earth once caved in on itself after voiding hundreds of cubic miles of molten rock in a matter of days. 3 eruptions, roughly 800,000 years and one 3 million years apart. And it has now been over 600,000 years since the last one. That gap is the number that keeps volcanologists awake at night, and it is also the number most frequently misunderstood by the public. A supervolcano does not run on a train schedule. There is no guarantee that a fourth eruption is overdue, simply because time has passed. But there's also no guarantee that the system has gone quiet forever. The uncomfortable truth sitting underneath all the scientific caution is this: nobody actually knows when it will happen again. And that uncertainty is precisely what makes Yellowstone one of the most closely monitored patches of ground on Earth. Every year, the Yellowstone Volcano Observatory records thousands of small earthquakes rippling through the region. Most are harmless, the normal creaking and shifting of a restless volcanic system. But scientists watch the patterns obsessively because a supervolcano preparing to erupt would very likely announce itself first through a swarm of intensifying seismic activity, followed by measurable ground deformation as magma pushes upward. In some recorded swarms, hundreds of small tremors have rattled through the park within a span of days, each one logged, plotted, and cross-referenced against decades of baseline data. And ground deformation is not hypothetical here. Parts of the Yellowstone caldera floor have been recorded rising and falling by measurable amounts over the decades, a slow breathing of the earth caused by shifting magma and hydrothermal fluids beneath the surface. In some years, the ground has risen several centimeters. In others, it has subsided. This restless motion is one of the clearest signs that the system beneath Yellowstone is very much alive. Entire sections of roadway inside the park have had to be repaired or rerouted over the years, simply because the ground itself refused to stay still. So what would actually happen if the unthinkable occurred? If Yellowstone produced another super eruption on the scale of its past 3? The immediate zone around the caldera would face annihilation on a scale that conventional disaster planning simply is not built for. Pyroclastic flows, superheated clouds of gas and volcanic debris that can move faster than 100 miles per hour, would obliterate everything within a radius of tens of miles almost instantly. Temperatures within these flows can exceed several hundred degrees Celsius, enough to incinerate anything organic in seconds. Entire towns, forests, and wildlife populations across parts of Wyoming, Montana, and Idaho would cease to exist within minutes of the eruption's onset. Rivers that once fed some of the most pristine wilderness in the country would run choked with ash and debris, their courses altered by landslides triggered in the eruption's first hours. But the immediate blast zone, as horrifying as it is, would ultimately affect a relatively small fraction of the country. The true continental catastrophe would come from what happens next: the ash. A Yellowstone supereruption would launch an enormous column of ash and volcanic gas miles into the atmosphere, where high-altitude winds would begin carrying it eastward across the United States. Modeling based on the ash distribution of the last supereruption suggests that a significant portion of the country, potentially stretching from the Rocky Mountains toward the Mississippi River and beyond, could receive a substantial layer of ash. In areas closer to the caldera, that layer could be measured in feet rather than inches. Cities hundreds of miles downwind could see skies darken in the middle of the day, streetlights flickering on as though dusk had arrived hours early. Ash of this kind is not like snow. It does not melt away or blow off harmlessly. Volcanic ash is made of tiny shards of pulverized rock and glass, abrasive enough to grind down machinery, contaminate water supplies, and collapse roofs under its sheer weight when wet. A few inches of it can be enough to ground every aircraft in a region, since ash ingested into jet engines can cause catastrophic failure. Farmland across the American breadbasket, the very fields responsible for a huge share of the country's grain production, could be smothered under a suffocating gray blanket, choking crops and starving livestock that depend on that land. Grain silos, irrigation systems, and harvesting equipment across multiple states would face damage that could take years, not months, to fully repair. Power grids would be especially vulnerable. Wet volcanic ash conducts electricity, and even a thin coating on power lines and transformers has been known to trigger widespread outages in past eruptions elsewhere in the world. Multiply that effect across several states simultaneously, and you begin to see how a Yellowstone eruption would not simply be a regional disaster. It would be a systemic shock to the electrical, agricultural, and transportation backbone of an entire nation. Hospitals running on backup generators, water treatment plants losing power, and communication networks going dark would all be plausible consequences unfolding at once, compounding faster than emergency responders could realistically address them. And this is where the story stops being about lava and starts being about something far more unsettling: the slow, grinding aftermath that could last for years. Supereruptions do not just reshape the land, they reshape the sky. When a volcano of this magnitude releases sulfur dioxide into the stratosphere, it can form a fine aerosol haze that reflects sunlight back into space. Historical eruptions far smaller than a Yellowstone supereruption have already demonstrated this effect. The 1991 eruption of Mount Pinatubo in the Philippines, for example, cooled global average temperatures by roughly half a degree Celsius for more than a year afterward. An even older comparison comes from 1815, when the eruption of Mount Tambora in present-day Indonesia caused what became known as the Year Without a Summer, a period of failed harvests, food shortages, and unseasonable frost across parts of Europe and North America. A Yellowstone-scale event, injecting vastly more material into the atmosphere than either of those eruptions, could trigger a far more severe and prolonged period of global cooling, sometimes referred to as volcanic winter. Crop failures driven by shortened growing seasons and reduced sunlight would ripple far beyond American borders. A nation already struggling to feed itself under a blanket of ash would now be contending with a planet struggling to grow food at all. Global supply chains, already fragile under far smaller shocks in recent history, would face a stress test unlike anything in modern memory. Nations that depend heavily on American grain exports would suddenly find themselves scrambling for alternatives that may simply not exist at the scale required, and the resulting price shocks could destabilize food security in regions thousands of miles from the eruption itself. It's worth pausing here to separate fact from fear, because this is exactly where the story tends to spiral into exaggeration online. Some viral claims suggest Yellowstone could erupt tomorrow, wipe out the entire United States in an instant, or plunge the world into an apocalyptic ice age lasting centuries. Volcanologists who study the site directly, including researchers with the United States Geological Survey, have repeatedly stated that there is no scientific evidence indicating an imminent eruption. The current probability of a Yellowstone supereruption occurring in any given year is estimated to be extremely low, statistically comparable to the odds of a large asteroid strike. But low probability is not the same as impossible, and it is certainly not the same as inconsequential. This is the paradox that makes Yellowstone such a compelling subject. It is simultaneously one of the least likely disasters on the horizon and one of the most catastrophic if it ever occurs. Emergency planners do not dismiss low probability, high consequence events. They plan for them precisely because the cost of being unprepared is almost unthinkable. So how exactly does the United States monitor a threat this immense? The Yellowstone Volcano Observatory, a consortium involving the United States Geological Survey, the National Park Service, and several university partners, operates a dense network of seismometers, GPS stations, and gas monitoring equipment across the region. This network tracks the subtlest tremors, the faintest shifts in ground elevation, and the smallest fluctuations in gas emissions from the park's geothermal features. Satellite radar interferometry adds another layer, allowing scientists to detect ground deformation across the entire caldera from space with remarkable precision. Data from these instruments streams continuously into monitoring centers, where automated systems flag anomalies long before a human analyst would ever notice them by eye. The goal of all this monitoring is early warning. Unlike an earthquake, which can strike with almost no notice, a supervolcanic eruption of Yellowstone's scale is expected to be preceded by weeks, possibly months, of escalating warning signs. Scientists anticipate that a genuine buildup toward eruption would involve a dramatic increase in seismic swarms, rapid and significant ground uplift, and shifts in the chemistry of gases escaping from hydrothermal vents. In other words, Yellowstone is unlikely to erupt as a total surprise. The far more realistic danger lies in whether warning signs would be interpreted correctly and acted upon quickly enough, especially given how rarely humanity has faced a threat of this exact nature in recorded history. And that raises an uncomfortable question that sits at the heart of every disaster case study. Even with warning, how do you actually evacuate a threat zone spanning multiple states? How do you move agricultural production, reroute critical infrastructure, and shelter a population against an ashfall event that could blanket a third of a continent? Highways designed for daily commuter traffic were never built to move millions of people and their livestock out of a danger zone within days. Fuel supplies, already strained under normal conditions, would face unprecedented demand at the exact moment ash-clogged engines and grounded aircraft made transportation dramatically harder. These are not questions with clean answers. They are the kind of questions that keep emergency management agencies running tabletop exercises rather than sleeping soundly. It is also worth understanding that Yellowstone is not the only volcanic system capable of large-scale eruption within the United States, though it remains the largest and most closely watched. The country's western volcanic arc includes numerous other active systems, from the Cascade Range volcanoes in the Pacific Northwest to smaller calderas scattered across the Rockies. Globally, other calderas carry similarly immense potential, including Indonesia's Toba, believed responsible for one of the largest eruptions in the last 2 million years, and Italy's Campi Flegrei, a restless volcanic field sitting uncomfortably close to the city of Naples. But none of America's other systems carry the sheer scale of potential consequence that Yellowstone does, which is precisely why it commands the lion's share of scientific attention and public fascination. There's also a psychological dimension to this story that deserves attention. Yellowstone occupies a strange place in the American imagination. It is simultaneously a beloved national park, a symbol of untouched wilderness, and a ticking geological question mark. Millions of tourists walk across its geyser basins every year, largely unaware that the very ground beneath their boots has, 3 times in Earth's history, unleashed devastation on a continental scale. That contrast between everyday tranquility and buried catastrophe is part of what makes the subject so magnetic. It is a reminder that some of the most dangerous forces on the planet do not announce themselves with menace. They hide in plain sight, disguised as beauty, wrapped in postcard-perfect scenery that draws families and photographers by the millions each summer. Consider too the sheer time scale involved. Human civilization as we understand it, agriculture, cities, written history spans roughly 10 to 12,000 years. The gap between Yellowstone's last 2 super eruptions was more than 600,000 years. On a geological clock, human history is barely a flicker. We have never, as a species, experienced a Yellowstone-scale eruption while living in organized civilizations with power grids, global trade, and 8 billion people to feed. Every past super eruption on this scale occurred before humans built the interconnected, fragile systems we now depend on for survival. That absence of precedent means our disaster models are, in many ways, educated extrapolations, rather than proven certainties, built from smaller historical eruptions and scaled upward through careful, cautious mathematics. This is precisely why scientific institutions invest so heavily in continuous monitoring rather than prediction based on historical timing alone. Researchers have increasingly moved away from framing Yellowstone's risk purely in terms of "it's overdue," a phrase that, while attention-grabbing, misrepresents how volcanic systems behave. Volcanoes are not obligated to follow the intervals of their past eruptions. Some volcanic systems have gone dormant far longer than expected, only to reactivate after centuries of apparent silence. Others show all the warning signs of unrest for generations, without ever culminating in an eruption. Yellowstone could remain quiet for another million years, or it could show alarming signs of change within our lifetimes. The honest scientific position is that both possibilities remain on the table, and pretending otherwise, in either direction, misrepresents the genuine uncertainty at play. What we do know is this: Yellowstone continues to breathe. Its geysers continue to erupt with startling regularity, a visible reminder of the immense heat churning below. Its earthquakes continue to be tracked, cataloged, and analyzed by scientists who have devoted careers to understanding a system that could, in theory, alter the trajectory of an entire civilization. And its magma chamber continues to sit beneath one of the most visited natural landmarks in the world, indifferent to the millions of footsteps crossing its surface every year. Beyond the physical destruction, there's an economic dimension to this story that rarely gets the attention it deserves. The United States sits at the center of global grain, soybean, and corn exports. And a significant share of that production comes from states that would fall directly within the projected ashfall zone of a Yellowstone supereruption. Insurance markets, agricultural futures, and international trade agreements are all built on the assumption of relatively stable harvests year after year. A single eruption capable of wiping out multiple growing seasons across a vast swath of the country would not simply dent the American economy, it would send shockwaves through commodity markets worldwide, driving up the price of staple foods in countries that have never even heard of Yellowstone and have no direct connection to the disaster itself. Insurance companies, many of which already struggle to price catastrophic, low-probability events accurately, would face claims on a scale that could bankrupt entire sectors of the industry. Then there is the question of population displacement, a challenge that modern disaster planning has never truly had to confront at this scale. Wildfires, hurricanes, and even major earthquakes typically displace populations numbering in the tens of thousands, occasionally reaching into the low millions for the most catastrophic events. A Yellowstone supereruption, by contrast, could render parts of several states uninhabitable for months or years, potentially displacing millions of people simultaneously. Where would they go? Who would house them? How would already strained housing markets in unaffected regions absorb a sudden influx of displaced families arriving with nothing but what they could carry? These are the kinds of second-order questions that rarely make it into viral headlines about supervolcanoes, yet they represent the true, grinding difficulty of recovering from an event of this magnitude. Media coverage of Yellowstone has not always helped clarify these realities. Documentary specials and online videos frequently blur the line between rigorous scientific modeling and speculative worst-case scenarios designed purely to generate views. Headlines proclaiming that Yellowstone is overdue, or that a mega eruption could happen any day, tend to omit the crucial context that volcanic recurrence intervals are not fixed schedules, and that the vast majority of seismic activity recorded at the site is entirely normal for an active geothermal system. This gap between sensational framing and careful scientific communication is itself part of the story, because it shapes how seriously the public, and by extension policymakers, take genuine warning signs when they do eventually appear. If people have been conditioned by years of exaggerated claims to assume every earthquake swarm signals imminent doom, there is a real risk that the actual warning signs, when they arrive, could be lost in a fog of desensitized skepticism. Scientists have tried to counter this by being unusually transparent about their monitoring data, publishing regular updates on seismic activity, ground deformation, and gas emissions for public review. This transparency serves a dual purpose. It reassures the public during periods of normal background activity, and it builds the kind of institutional trust that would be essential if warning signs ever did escalate towards something genuinely concerning. Trust, it turns out, may be one of the most underrated tools in disaster preparedness. A population that dismisses every warning as exaggerated is just as vulnerable as a population that panics at every false alarm. There is a quieter, more immediate hazard as well, one that rarely makes headlines, but has already caused real harm. Yellowstone's hydrothermal features, the same geysers and hot springs that draw crowds every summer, are themselves capable of sudden, violent explosions unrelated to a full magmatic eruption. These hydrothermal explosions occur when trapped water flashes instantly into steam, hurling rock and boiling water into the air with little to no warning. Craters left behind by past hydrothermal explosions dot the landscape, some large enough to swallow a house. It is a sobering reminder that even without a supereruption, the ground beneath Yellowstone is capable of violence on a much smaller but still dangerous human timescale. It also helps to understand what science actually means when it uses the word supervolcano, because the term itself has become so overused in popular media that its precision often gets lost. Volcanologists classify eruptions using the Volcanic Explosivity Index, a logarithmic scale that measures the volume of material ejected during an eruption. A supervolcano, by strict definition, is a volcanic system capable of producing an eruption that registers an 8 on this scale, the highest classification that exists, representing the ejection of more than 1,000 cubic kilometers of material in a single event. Only a small handful of known volcanic systems on Earth have ever produced eruptions of this magnitude, and Yellowstone's past 3 eruptions all sit within or near that extreme category. This is part of why the site draws such intense scientific interest. It is not simply a large volcano, it belongs to an exceptionally rare class of geological events that has shaped the planet's climate and ecosystems on a scale most other natural disasters simply cannot match. It's also worth examining how researchers actually reconstruct these ancient eruptions in the first place, since none of them were witnessed by anyone capable of writing them down. Geologists piece together the story of Yellowstone's past through layers of volcanic rock called ignimbrite, hardened deposits left behind by pyroclastic flows that can be dated using radiometric techniques measuring the decay of natural elements within volcanic minerals. By studying the thickness, composition, and geographic spread of these deposits across the American West, scientists can estimate not only when past eruptions occurred, but roughly how large they were, and in which directions the debris traveled. Ashfall layers, found in sediment cores as far away as the Gulf Coast, and even offshore in ocean sediment, have allowed researchers to map the staggering reach of Yellowstone's past eruptions with remarkable geographic detail, essentially reading a 3-million-year diary written in stone and ash. This kind of forensic geology also helps refine the models used to predict what a future eruption might look like. Rather than relying purely on worst-case theoretical calculations, scientists calibrate their ashfall and climate impact models against what actually happened during Yellowstone's documented eruptions, adjusting for changes in prevailing wind patterns, atmospheric composition, and the layout of modern infrastructure that simply did not exist hundreds of thousands of years ago. It is a strange kind of science, one that requires reconstructing catastrophic events from the deep past in order to anticipate a catastrophe that has never happened within the memory of civilization. None of this diminishes the very real, very human anxiety that surrounds the subject. There is something uniquely unsettling about a threat that cannot be negotiated with, evacuated from in the traditional sense, or mitigated through engineering the way a coastal community might build seawalls against rising water. A hurricane can be tracked days in advance with a fairly reliable projected path. A Yellowstone supereruption, should it ever occur, would emerge from decades or centuries of subtle, ambiguous signals that even trained scientists might struggle to interpret with full confidence until the process was already well underway. That combination of enormous consequence and genuine scientific uncertainty is exactly what has cemented Yellowstone's place in the public imagination as something between a scientific curiosity and a slow-motion nightmare. Perhaps the most sobering realization in all of this is not the eruption itself, but what it reveals about the limits of human control. We can build satellites that track ground deformation to the millimeter. We can install seismometers sensitive enough to detect tremors imperceptible to human senses. We can model ashfall patterns with extraordinary precision using historical eruption data. But when it comes to a force capable of reshaping a continent, all of that technology amounts to sophisticated observation, not command. We can watch, we can prepare, we cannot stop it. And so the question that lingers, the one that has no comfortable answer, is simply this. If the ground beneath Yellowstone begins to shift in ways we have never seen before, will we recognize the signs in time? And will recognizing them even be enough? Some researchers have begun exploring more speculative ideas around this very question, including proposals to gradually extract heat from the magma system as a way of both monitoring it more directly and, in theory, slowly reducing pressure over extraordinarily long timescales. Such proposals remain largely theoretical and controversial within the scientific community, carrying their own risks that are not yet fully understood. Drilling into an active volcanic system, even for research purposes, raises questions about triggering effects that no one can fully model in advance. For now, these ideas remain confined to academic papers and cautious speculation rather than any active engineering effort, a reminder that even our most ambitious proposed solutions are still, at best, tentative steps into unknown territory. What ultimately makes Yellowstone such a compelling subject is not just the scale of the potential disaster, but the strange coexistence of wonder and dread that defines the place. Families picnic within sight of geysers that are direct evidence of the very system capable of continental devastation. Photographers wait patiently for the perfect shot of Old Faithful, unaware, or perhaps simply unbothered, that they are standing atop the collapsed remnant of one of the largest explosions in the planet's recent geological history. This duality, the postcard beauty layered directly over profound danger, is not something audiences encounter often, and it is precisely what continues to draw scientists, storytellers, and casual travelers back to the same patch of American wilderness, year after year, each one walking across a landscape still quietly deciding its own future. For now, the geysers keep erupting on schedule. The tourists keep taking their photographs. Rangers keep monitoring their instruments, logging every tremor into a growing archive that stretches back decades. And deep beneath the surface, in a chamber of molten rock larger than most people could ever imagine, the slow, patient forces that shaped this landscape 3 times before continue their quiet, unresolved wait.